Welcome back to the Nocturnal Astronomer. My name is Atlas Reed, and I will be your guide through the deep. Tonight, we are going somewhere that most people never think to look. Not at a single star, not at a single galaxy, not even at a single cluster of galaxies. Tonight, we are going to look at the biggest things that have ever existed. We are going to trace the shape of the universe itself, the great walls of galaxies that stretch for billions of light years, the invisible threads that hold the cosmos together, the colossal empty regions so vast that they beg a description. And through all of it, I want you to feel something that I think is quite rare and quite beautiful. I want you to feel genuinely, profoundly, peacefully small. Let's dive in. Part 1. A question of scale. Before we can understand the largest structures in the universe, we have to recalibrate our sense of scale almost entirely. The human mind is built to understand distances measured in steps, in miles, in the span of a country. The universe does not operate at those scales. The distance from Earth to the Moon is roughly 250,000 miles. That is a number most people find difficult to truly feel. Now imagine travelling that distance not once, but millions of times. That begins to approach the scale of a single galaxy. Our own galaxy, the Milky Way, is about 100,000 light years across. A light year is the distance light travels in a full year, moving at roughly 186,000 miles every second. The Milky Way is not a small thing. It contains somewhere between 200 billion and 400 billion stars. And yet, the Milky Way is utterly unremarkable in size. There are galaxies many times larger. There are galaxies so vast that our entire galaxy would appear as a minor suburb on their outskirts. This is the first step toward comprehending the structures we are going to discuss tonight. The structures we are building toward are not made of single stars. They are not made of single galaxies. They are made of galaxy clusters. And those clusters are themselves assembled into even larger groupings. And those groupings are threaded through by forces we are only beginning to understand. If a star were the size of a grain of sand, a galaxy would be roughly the size of a continent. And the structures we are going to talk about tonight would be the size of the planet itself, or larger. Scale is not just a number here. It is a different way of thinking. Human civilizations have risen and fallen in spans of a few thousand years. The light from some of the galaxies we will discuss tonight began its journey toward us before the Earth existed. Some of it began traveling before our sun had even ignited. We are looking back through time simply by looking out into outer space. This is one of the stranger gifts that astronomy offers. Every telescope is a time machine. The farther you look, the older the image becomes. The structures we are going to trace across the sky tonight are not just large, they are ancient beyond any comfortable reckoning. So, as you settle in and let the voice carry you forward, try to hold this thought loosely. Everything familiar, everything human, everything that has ever been built or sung or spoken fits inside a space that the universe would barely notice. And somehow, that is not a frightening thought. It is a deeply restful one. We begin then, not with the largest structure, but with the building block, the humble, enormous, almost incomprehensibly vast building block from which all larger things are made. We begin with the galaxy cluster. Part 2. Galaxy clusters. A galaxy cluster is exactly what its name suggests. It is a gathering of galaxies held together by gravity, orbiting a shared center of mass, bound to one another across distances measured in millions of light years. They are the largest objects in the universe, held together by their own gravity. The cluster nearest to us is called the Virgo cluster. It sits roughly 53 million light years away and contains somewhere between 1,300 and 2,000 galaxies. Our own Milky Way is not part of it, though it and our local neighborhood feel a gentle gravitational pull from the Virgo cluster's enormous mass. The mass of a galaxy cluster is almost impossible to state in any unit that feels meaningful. The Virgo cluster alone contains mass equivalent to roughly 1 quadrillion suns. Written out, that is a 1 followed by 15 zeros. All of that mass, much of it invisible, packed into a region of space tens of millions of light years across. Most of the mass in a galaxy cluster is not in the galaxies themselves. It is in 2 other forms. One is a diffuse hot gas that fills the space between galaxies, so superheated that it glows in X-ray light. The other is dark matter, which we cannot see at all, but can detect through the effect it has on the motion of visible matter around it. Imagine filling a room with a gas so hot it becomes invisible to the naked eye, and then imagine that most of the furniture in the room is also invisible, detectable only by the way it causes other furniture to move. That is roughly the situation inside a galaxy cluster. The visible galaxies are the minority. Some galaxy clusters are extraordinarily large. Among the most massive known is a cluster sometimes called El Gordo, which means the fat one in Spanish. It sits far across the universe and was found to have a mass roughly 3 million billion times the mass mass of our Sun when it was first studied. It is one of the most massive clusters ever discovered. Galaxy clusters are also dynamic. They collide with one another. These are not fast, dramatic impacts in the way a film might depict a crash. They unfold over hundreds of millions of years, with vast clouds of gas slamming together and superheating, while the galaxies themselves mostly pass through one another, like two clouds of gnats merging on a still evening. The collision of galaxy clusters produces some of the most energetic events in the universe since the Big Bang. Shock waves travel through the hot gas. The dark matter in each cluster, not interacting electromagnetically the way gas does, passes through and moves ahead of the gas. Observations of these collisions have provided some of the strongest evidence we have for the existence of dark matter. And yet, with all of this, a galaxy cluster is still just a stepping stone. It is a building block. A galaxy cluster is to a supercluster what a city block is to a continent. We have only just begun to climb toward the scales we are ultimately reaching for tonight. The clusters themselves are arranged not randomly, but in vast chains and sheets. They are the beads on strings that form the skeleton of something far larger. They are the first hint of a pattern, a shape to the universe that only becomes visible when you step back far enough to see the whole. Part 3. Superclusters. A supercluster is a collection of galaxy clusters and galaxy groups gathered together into a larger gravitational neighborhood. They are not bound together the way a cluster is. The clusters within a supercluster are not necessarily falling toward a shared center, but they are connected, related, part of the same vast structure. For many decades, the structure we call the local supercluster, or the Virgo supercluster, was considered our cosmic home at the largest scale. It contains our own local group of galaxies, along with dozens of other groups and clusters, spread across a region roughly 110 million light-years across. That picture changed in 2014, when a team of astronomers redrew our understanding of what the local supercluster actually is. Using measurements of how galaxies move through space, they traced the paths of thousands of galaxies and found that they were all flowing on the largest scales toward a single gravitational basin. This vast region, which they named Laniakea, which means immeasurable heaven in Hawaiian, contains the equivalent of roughly 100 million billion solar masses. It spans about 520 million light-years. It includes the Virgo cluster, hundreds of other clusters, and roughly 100,000 galaxies, including our own. Laniakea is not a thing in the way a star or a planet is a thing. It is more like a watershed. Just as all the rain that falls on one side of a mountain range flows toward the same sea, all the galaxies within Laniakea are being pulled very slowly toward a point astronomers call the Great Attractor. The Great Attractor is a region of gravitational attraction deep within Laniakea. It is not a single object. It is a concentration of mass, most of it unseen, that exerts an enormous pull on everything in our cosmic neighborhood. Our own galaxy, along with billions of others, is drifting toward it at roughly 600 kilometers per second. For a long time, studying the Great Attractor was difficult because it lies in a direction obscured by the disk of our own Milky Way. The stars and dust of our galaxy block our view of the region behind it. Only with instruments that look in wavelengths other than visible light have astronomers been able to begin mapping what lies there. What they found was a massive cluster of galaxies at the heart of the attraction, though even that cluster does not fully account for the gravitational pull. There is likely much more matter, most of it dark, contributing to the flow. The full picture is still being assembled, piece by careful piece. Laniakea is not alone. There are other superclusters distributed throughout the observable universe. The Perseus supercluster, the Coma supercluster, the Shapley supercluster, which is one of the most massive concentrations of galaxies in our part of the universe, and adds its own gravitational tug to the flows of nearby clusters. And all of these superclusters are themselves arranged, not scattered randomly, but laid out in a vast and intricate pattern. To see that pattern, we need to step back even further. We need to zoom out to a scale where even superclusters become small, where the entire landscape of the universe begins to reveal its true shape. Part 4. The Cosmic Web. When astronomers began to map the large-scale structure of the universe in earnest, using surveys that catalogued hundreds of thousands and eventually millions of galaxies, something remarkable emerged from the data. The universe is not smooth. It is not uniform. It has a texture. Galaxies are not spread evenly through space, the way seeds scattered on a table might be. They cluster. They collect into chains and sheets. And between these chains and sheets are enormous regions of near emptiness. The universe, at the largest scales, looks like a cosmic web. The analogy most often used is that of a sponge or of soap bubbles packed tightly together. The material, the galaxies and clusters and gas, exists primarily at the intersections and along the surfaces. The interiors of the bubbles are largely empty. The structure has been confirmed repeatedly across increasingly deep surveys of the sky. The threads of this web are called filaments. They are the long, thin, tendril-like structures along which galaxies accumulate. A filament might stretch for hundreds of millions of light years, containing thousands of galaxies lined up along its length like lights along a highway seen from high above at night. Where filaments cross, or where several converge, the density spikes dramatically. These are the nodes of the web, the most crowded intersections, and they are where the largest galaxy clusters tend to be found. The Virgo cluster, the Coma cluster, and other massive concentrations sit at these crossroads. The web is not static, it is growing. Dark energy is causing the universe to expand, and as it does, the already empty regions between filaments grow larger and emptier, while the filaments themselves continue to funnel matter toward the nodes. The web is like a net that is slowly being stretched across a widening surface. This structure was not random. It grew from tiny quantum fluctuations in the earliest moments of the universe. In the first fraction of a second after the Big Bang, there were infinitesimally small variations in density across space. Over billions of years, gravity amplified those variations. Dense regions attracted more matter. Empty regions shed more matter. The web is the result. Computer simulations that model the evolution of the universe from its earliest moments forward in time produce structures that look strikingly similar to what we observe. The cosmic web, in other words, is not just a description of how galaxies happen to be arranged. It is the inevitable consequence of the physics of the Big Bang and of gravity working across cosmic time. The web has been seen not just in the distribution of galaxies, but in the distribution of gas between galaxies. Astronomers have detected faint filaments of hydrogen connecting galaxy clusters, enormous bridges of diffuse material following the same skeleton that galaxies trace. The web is real, and it is everywhere. Now that we have this framework in mind, this picture of filaments and nodes and vast empty bubbles, we can begin to look at the largest individual structures within it, the single biggest walls, the single biggest filaments, the single biggest known features on the cosmic map. We are approaching the edge of what has been charted. Part 5. Great Walls. Within the cosmic web, certain structures stand out even against the enormous backdrop of filaments and clusters. These are the Great Walls, the grand sheets of galaxies that form some of the most striking features in any map of the large-scale universe. They are, in many cases, the largest coherent structures we have ever identified. The first of these to be discovered was found in the 1980s when astronomers Margaret Geller and John Huchra were conducting one of the early systematic surveys of galaxy positions in 3 dimensions. They found something that looked, in cross-section, like the stick figure of a person. It was called the Stickman. That feature was part of what became known as the CFA Great Wall, named for the Center for Astrophysics, where Geller and Huchra worked. It spans roughly 500 million light-years across and about 200 million light-years tall. At the time of its discovery, it was the largest known structure in the universe. It did not hold that distinction for long. In the early 1990s, another survey revealed the Sculptor Wall, and surveys continued to push the boundaries outward. Each new map of the sky showed that the walls and structures astronomers were finding were not isolated features, but parts of a larger and larger tapestry. Then, in 2003, astronomers announced the discovery of the Sloan Great Wall, found in data from the Sloan Digital Sky Survey, one of the most comprehensive maps of the sky ever assembled. The Sloan Great Wall stretched for roughly 1.37 billion light-years, making it the largest known structure at the time of its discovery. 1.37 billion light-years. Light, traveling at the fastest speed anything in the universe can move, would take 1,370,000,000 years to cross that single structure from one end to the other. The Earth had not yet formed when that journey would have begun. The dinosaurs had not yet appeared when it would have been halfway done. Even the Sloan Great Wall would eventually be surpassed. Surveys reached deeper and wider, and astronomers began finding structures that challenged the theoretical models of how large, coherent structures could be. According to many cosmological models, the universe should be essentially uniform at very large scales, and yet the maps kept revealing features that pushed those boundaries. The Great Walls are sheets of galaxies, in the same way that a soap bubble surface is a sheet. They are not solid in any conventional sense. The space between galaxies within a great wall is still enormous, but compared to the vast voids on either side of them, they are densely populated neighborhoods. Detecting these structures requires not just observing light from galaxies, but measuring the distance to each one, which is done using a property called redshift, the stretching of light caused by the expansion of the universe. The further a galaxy is, the more its light has been stretched, and the more that stretch can be measured, the more precisely its distance can be calculated. The technology to do this at scale, to measure the redshifts of millions of galaxies across the sky, was decades in the making. The Great Walls existed long before we could see them. They were always there, in the dark, enormous and patient, and utterly indifferent to whether anything in the universe would ever take note of them. Part 6. The Great Wall Beyond. In 2013, a team of astronomers announced the discovery of a structure that left many in the field genuinely unsettled. Not because it was impossible, but because it was so large that it challenged the standard picture of how the universe should look at very large scales. The structure is called the Hercules Corona Borealis Great Wall, named for the two constellations in the direction of which it appears from Earth. It was found not through a survey of galaxy positions, but through the distribution of gamma-ray bursts, the most energetic explosions in the universe, which can be detected across almost unimaginable distances. Gamma-ray bursts are thought to occur in star-forming galaxies, and so their distribution traces the distribution of galaxies, even in regions too distant for galaxy surveys to reach in detail. When the team analyzed a large collection of gamma-ray burst positions, they found a region of sky where the bursts were concentrated in a way that suggested an underlying structure of extraordinary size. The estimated span of the Hercules Corona Borealis Great Wall is roughly 10 billion light years. That is not a typo or an exaggeration. 10 billion light years. The observable universe is about 93 billion light years across, and this single structure spans something like a tenth of that total span. To put that in terms of time, light leaving one end of this structure, headed for the other end, began its journey when the universe itself was less than 4 billion years old. The sun had not yet formed. It would not form for another several billion years, and that light is still traveling. It has not arrived. The discovery generated significant debate. The standard cosmological model, which describes how the universe's matter should be distributed at large scales, suggests that no structure larger than roughly 1.2 billion light years should exist. The Hercules Corona Borealis Great Wall is roughly 8 times that theoretical limit. Some researchers have argued that the statistical methods used to identify the structure need further refinement, that the apparent concentration in gamma-ray burst positions might be partly an artifact of how the data was gathered or analyzed. The debate is ongoing, which is how science works at its edges. But even in the most conservative interpretations, the region in question represents a departure from the uniform distribution the standard model predicts. Whether it is the most massive single structure ever found, or a somewhat smaller but still enormous feature, it points toward a universe that may have more large-scale architecture than our best models currently account for. The implications are significant. If the Hercules Corona Borealis Great Wall is confirmed at its estimated scale, it would require either a revision of the standard cosmological model or an explanation for why the early universe contained fluctuations large enough to seed a structure of this magnitude over the billions of years since the Big Bang. Either way, the universe appears to be telling us that our maps are still incomplete, that the largest features on the cosmic landscape are still coming into focus, and that the story of how everything is arranged is considerably more complex and more surprising than we initially imagined. The Hercules Corona Borealis Great Wall is a humbling frontier. Part 7. Cosmic Voids. We have been talking about where matter is, but to understand the full shape of the universe, we also need to talk about where matter is not. The voids, the vast and largely empty regions that take up most of the volume of the observable universe, are in their own way as extraordinary as the Great Walls. A cosmic void is not a perfect vacuum. There are galaxies within voids, but the density of galaxies inside a void is far lower than in the filaments and walls that surround them. Voids are the empty interiors of the cosmic web's bubbles, the regions that have been draining of matter for billions of years as gravity pulled everything toward the denser surrounding structures. The largest confirmed void in the relatively nearby universe is called the Boötes Void, sometimes informally called the Great Nothing. It was discovered in 1981 and sits roughly 700 million light-years from Earth. It spans approximately 330 million light-years across. 330 million light-years of near emptiness. If the Milky Way were located at the center of the Boötes Void, we would not have known that other galaxies existed until the 1960s. The nearest other galaxies would have been so far away that our radio transmissions, which began in earnest in the early 20th century, would not yet have had time to reach them. That thought is worth sitting with. The discovery that we are not alone in the universe, that other galaxies exist beyond our own, happened in the 1920s. If we had been born in the heart of the Boötes Void, it would have taken us decades longer simply to gather the evidence. The void would have hidden the cosmos from us, at least for a while. The Boötes Void appears to be anomalously large for its kind. Standard models suggest that a void of that size should contain several dozen smaller voids that have merged over time. And indeed, there is some evidence that the Boötes Void is the result of many smaller voids having merged together, which would make it more consistent with theoretical predictions. Voids are not static. They grow. As the universe expands, dark energy accelerates that expansion, and voids in particular tend to grow faster than average because there is less matter within them to resist the expansion. The filaments surrounding voids are slowly being stretched thinner. The voids are slowly growing larger. There is also a remarkable phenomenon associated with voids called the integrated Sachs-Wolf effect. As light from the early universe passes through a void, it gains a tiny amount of energy entering the void, and then loses a nearly equal amount leaving it. But because the void is expanding while the light is crossing it, the gain and loss do not perfectly cancel. The light emerges very slightly warmer. This effect has been detected. Astronomers have been able to correlate the positions of large voids with subtle warm spots in the afterglow of the Big Bang, the cosmic microwave background radiation, which is the faint thermal echo of the universe's earliest moments, still visible in every direction we look. Voids leave their fingerprints on the oldest light in the cosmos. And there may be voids far larger than the Boötes void. At greater distances, mapping voids becomes more difficult, but the statistical signatures of very large empty regions have been identified in several surveys. The universe is mostly emptiness. The filaments and walls and clusters that we find so remarkable are, in terms of pure volume, the minority. Part 8. The Cold Spot. Among the most intriguing features in the large-scale structure of the universe is one that we did not find by looking at galaxies at all. We found it by looking at the oldest light in existence, the cosmic microwave background radiation, the faint glow left over from when the universe was just 380,000 years old. The cosmic microwave background is extraordinarily uniform. In every direction we look, it is almost exactly the same temperature, about 2.7 degrees above absolute zero. The tiny variations that do exist, fluctuations of roughly 1 part in 100,000, are what eventually grew into all the structure we see today. But in data collected by a space mission called the Wilkinson Microwave Anisotropy Probe, and confirmed by subsequent missions, astronomers found a feature that was larger and colder than their models predicted. A region of sky in the direction of the constellation Eridanus was measurably cooler than the surrounding area. This feature became known simply as the cold spot. It spans about 5 degrees across the sky, which corresponds to a physical region of enormous size, and it is colder than its surroundings by about 70 microkelvins. That is an almost incomprehensibly small temperature difference, and yet it is statistically significant. Several explanations have been proposed for the cold spot. One early suggestion was that it might represent an enormous void, a supervoid, whose effect on light passing through it would produce exactly the kind of cooling signature observed. A very large supervoid would leave its mark on the microwave background through the same integrated Sachs-Wolf effect mentioned earlier. In 2015, a team of astronomers announced that they had found strong evidence for just such a supervoid in the direction of the cold spot. The void they identified spans roughly 1.8 billion light-years and sits about 3 billion light-years from Earth. It is one of the largest individual voids ever identified. However, subsequent analyses found that even a supervoid of that size would not fully account for the depth of the cold spot's temperature anomaly. There may be additional contributing factors, or the statistical significance of the cold spot may be somewhat overstated, or there may be physics at work that is not fully captured by current models. Some researchers have proposed more exotic explanations. One suggestion, which is speculative but not without theoretical grounding, is that the cold spot might be the imprint of a collision between our universe and another universe in a broader multiverse. If such a collision had occurred in the very earliest moments of the Big Bang, it might have left a cold circular imprint on the microwave background. This explanation remains highly speculative and is not supported by the mainstream consensus, but it illustrates something important about the cold spot. It is one of those features of the universe that sits right at the edge of our understanding, where the data is real and the anomaly is confirmed, but the explanation remains genuinely open. The cold spot and the supervoid associated with it remind us that the large-scale structure of the universe is not just a beautiful pattern to be admired from a distance. It is a record of the universe's history, written in the distribution of matter and in the temperature of ancient light, and it continues to hold mysteries that our current theories have not yet fully resolved. Part 9. Dark Matter's Invisible Hand. All of the structures we have been discussing, the filaments, the walls, the clusters, the voids, would not exist in their current form without a substance that we cannot see, cannot touch, and cannot detect directly with any instrument built to date. This substance is dark matter, and it is the invisible scaffolding on which all visible structure is built. Dark matter is not a new idea. Its existence was first seriously proposed in the 1930s by the astronomer Fritz Zwicky, who found that the galaxies in a large cluster were moving far too fast to be held together by the gravity of their visible mass alone. Something else had to be providing additional gravitational pull. He called it Dunkel Materie, dark matter. The evidence has grown overwhelming since then. Galaxies spin at rates that require far more mass than is visible. The bending of light by large masses, a phenomenon called gravitational lensing, consistently shows more mass than can be accounted for by stars and gas. The structure of the cosmic web itself matches simulations only when dark matter is included. Dark matter does not interact with light. It does not emit it, absorb it, or reflect it. It interacts only through gravity. This is why we cannot see it directly. We can only infer its presence from the way it moves other things. The way a wind in a room might be inferred from watching curtains move, even when the air itself is invisible. The current best estimate is that dark matter makes up roughly 27% of the total energy content of the universe. Ordinary matter, all the stars, planets, gas, dust, and every atom of everything that can be directly observed, makes up only about 5%. The remaining 68% is dark energy, which is responsible for the accelerating expansion of the universe. In the context of the cosmic web, dark matter played the decisive role. In the earliest moments of the universe, dark matter began clustering under its own gravity, even before ordinary matter could. It formed the invisible skeleton, a web of dark matter filaments and halos, before the visible web of galaxies followed. Ordinary matter fell into the gravitational wells already carved by dark matter. Think of it as a set of riverbanks carved into a landscape before any water flows. The dark matter shaped the channels, and then the visible matter, the gas that eventually formed stars and galaxies, flowed into those channels and followed their contours. The cosmic web we observe is, in a sense, just the visible part of a deeper dark matter web beneath it. The largest structures in the universe, the superclusters, the great walls, the grand filaments, are all sitting in peaks of the dark matter distribution. The voids correspond to the troughs. If we could somehow map the dark matter directly, we would see a web whose shape closely mirrors the galaxy distribution, but is smoother, its features more evenly blended. Despite decades of searching, no particle experiment on Earth has yet directly detected a dark matter particle. Dozens of candidates have been proposed and ruled out. New experiments continue to push the boundaries of sensitivity. The nature of dark matter, what it actually is at the particle level, remains one of the deepest open questions in all of physics. And yet, regardless of what dark matter turns out to be at the fundamental level, its role in shaping the universe is not in doubt. It is the invisible hand that gathered matter from the earliest moments of cosmic history and arranged it over billions of years into the magnificent structures we see tonight. Without it, none of what we have discussed would exist. Part 10. The Edge of the Map. We have travelled a long way tonight, from galaxy clusters to superclusters, from the cosmic web to great walls spanning billions of light years, from the cold spots on ancient light to the invisible matter that shaped everything. Now, at the end of this journey, let us sit for a moment at the edge of the known map. The observable universe is a sphere about 93 billion light-years across. That boundary is set not by the edge of everything that exists, but by the distance light has had time to travel to us since the Big Bang. Beyond that that sphere, there is almost certainly more universe, possibly far, far more. But we cannot observe it. Within that sphere, astronomers have catalogued roughly 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star is itself a nuclear engine burning for millions to billions of years. The scales involved are so far beyond ordinary human intuition that no analogy really does them justice. And yet, somehow, the universe managed to organize all of that into a pattern. The cosmic web, the filaments and walls and voids, emerged from the physics of the Big Bang and the long, patient action of gravity. There is an order to the cosmos at the largest scales, even if that order is not yet fully understood. New surveys are being conducted right now that will map the universe's structure in unprecedented detail. The Euclid Space Telescope, launched in 2023, is designed to map billions of galaxies across a significant portion of the sky and use their distribution to probe the nature of dark matter and dark energy. It is the most ambitious large-scale structure survey ever attempted. Future surveys will push further still, reaching deeper into the universe and further back in time, mapping the cosmic web as it appeared when the universe was younger, when the filaments were thinner and the clusters were still assembling themselves from smaller pieces. We will be able to watch the web being woven in slow motion across cosmic time. There is a concept in astronomy called the end of the observable universe, not as a physical place, but as a practical limit. As the universe expands, driven by dark energy, galaxies beyond a certain distance are being carried away from us faster than light can travel. They are receding, not because they are moving through space, but because space itself is expanding. The most distant galaxies we can currently observe are already, right now, being carried beyond our reach. Future civilizations in the far future of this universe will look out on a sky with fewer and fewer observable galaxies. The cosmic web will still exist, but more and more of it will be beyond the horizon, invisible, unreachable, lost to the expansion. There is something profound in that. The universe is, in a sense, slowly erasing itself from our view. The moment we happen to exist in is, cosmologically speaking, a fortunate one. We can still see nearly 2 trillion galaxies. We can still trace the filaments. We can still glimpse the great walls. We came along at just the right time to see the map while it is still mostly complete. And in all of that, in the quadrillions of solar masses and the billions of light years and the invisible dark scaffolding and the ancient cold light and the walls of galaxies older than the sun, there is a kind of stillness. The universe, for all its violence and scale, is mostly quiet, mostly empty, mostly dark, And if you let yourself feel it, that is not a frightening thing. It is a peaceful one. And on that note, we come to the end of tonight's journey through the largest structures in the observable universe. From galaxy clusters to superclusters, from the threads of the cosmic web to great walls stretching across billions of light years, from the vast empty voids to the invisible dark matter that weaves it all together. I hope that somewhere in all of that you found the particular kind of rest that only vastness can provide, the kind that comes not from certainty, but from wonder, not from answers, but from the sheer size of the questions. The universe is larger than we can hold in mind, and somehow that is enough. Thank you for joining me tonight on the Nocturnal Astronomer. Wherever you are, whatever the hour, I hope the dark is a little softer and the quiet a little wider. Until next time,